All right, so this is our first video of Test 3 material. This video also needs to kind of give you some background, introduction to a couple of the topics that you're going to be learning over the next week. So with that said, the first half of the video might seem a little confusing, but hang in there. At the end, we're actually going to work a problem, and you're going to see how it's actually pretty simple to work this new material. But let's get really organized first. Some of you just take notes off of my video and you don't look at the lecture notes that I have loaded to go with the video. Please do that, because there are 3 handouts that you're not going to be able to find on Canvas anywhere as part of those lecture notes, and you are going to need those handouts for videos that you watch in the future. So you need to go ahead and pause me right now and go print them. Obviously, probably the first 3 pages of the lecture notes are actually lecture notes, and then these are the 3 handouts. There's one that looks very sloppy. It's kind of supposed to. It's my handwriting. There's one that has 2 problems Xeroxed from a textbook. And then there is a neater handwritten something about political polls. So you absolutely need these 3 handouts printed so you can have them for other videos. Okay. We do not need them for the video today, but I suggest you print them because you're going to forget where to find them. Also, as we're getting organized, you do need this for the video today. You need to have your Z-chart out. You would have been using that for test 2. If you wrote all over yours, print another one. I tried to reload a better copy, particularly if you print it in pretty good quality. It should be very readable. And then part of the cheat sheet file is this. It has a bunch of formulas on it. I'm going to be pointing to 2 formulas right down there today, so that way you'll always know what and where things are on the cheat sheet that I provide for you. All right, let's see. That can be put away. Okay. So we're in chapter 6.3, sampling distribution of the sample mean. So particularly at this point, I'm going to be throwing up letters, notation, and I'm going to expect that you know what it means. When I write up mu, you need to know that that stands for the population mean. When I write up xbar, you need to know that stands for the sample mean. When I write up S, that is the sample standard deviation. I'm kind of looking through. We're still going to be using our z-score formula, x minus mu over sigma. We're going to tweak it a little bit, but, oh yes, and then of course sigma is population standard deviation. Okay, so if you're still struggling with that notation, you have to know it like you know your first name. All right, I'm going to turn this towards me because if we're in the classroom, you guys watch me ramble for about 10 minutes, then I write some stuff on the board. So we're going to try to, there I am, recreate that. Up until this moment right now, basically what you came off of from test 2 has been studying the individuals. That's why we used to call it X, right? We would turn X's into Z's and then get the areas, the probabilities. But it was studying the individual. Now, while that was really important, that's not quite the way real life works. From this point forward is what statistics really is. Using the sample, fix my hair here, to help you estimate the population, right? So let me just talk through a brief example. And I need my calculator. Sorry, hold on. I didn't want to show you my messy room. 20,000 JMU students, okay? Let's say we wanted to know or try to help estimate the true SAT score for those students. Now, up until this point, all we would have had available was to ask one student, what's your SAT score? And use that as an estimate of the population. You can kind of see that seems pretty dangerous, right? One student, what about if I get the one genius? Well, that's not representative of all of JMU. What about if I get the person who totally tanked it? They're just a terrible test taker. They hadn't gotten any sleep. That's not representative of JMU, right? So it's got to be something better than that. Well, let's work our way up. Let's say I take a sample of 5 students. All right, well, that's better. Even if I get the genius in there, these other 4 students are going to help balance it out. I mean, yes, we did talk about skewed data, but at least there's 4 other students helping balance out the genius, right? So it would be a little bit better. Well, all right, let's up that. Let's take 10 students in our sample. That's better than 5 students, right? So now, in case you have, I guess I made my thumb, in case you have the genius in there, you have 9 other students kind of balancing it out, right? All right, so 10 students, better than 5. 5 students, better than 1. Well, yes, we can keep doing that. I don't have enough fingers, right? Let's say we take 100 students. Oh, that's a whole lot better than taking just 10 students. So you already probably have an intuitive common sense feel that taking a sample of students and finding their xbar, their sample mean, SAT score, is much better than just relying on the one student, right? And the larger the sample you take, the better, because you have more information coming in and outliers wouldn't have as much effect. Okay, but all right, we're up to 100. Well, let's take 1,000. That's got to be better than 100. Yeah. All right, let's take 5,000 students as a sample. Well, yes, that's better than 1,000. Well, at some point, I can get up to all 20,000, and that's called the population. So, but why didn't we do the population to begin with? That's what we talked about on day 2. It's all about time and money and logistics, and can I even logistically do it, right? So there has to be some sweet spot, some sample size that is doing enough good statistics that we need it to do, but is still cost effective, that is still possible to do in real life. And you're actually going to see today that most of the time, depending on what we're studying, but most of the time that magic number is 30. So we don't have to take 10,000. Now, my 30 you're going to see is because my example so far has been about measurement data, but while I'm just giving you a brief intro, and particularly we're in the middle of polling season, right? And election season. Political polls are basically yes/no questions, right? They're pretty much categorical, proportions. We're going to talk about that in the next video, but as an intro, you're basically asking people, are you going to vote for Biden, yes or no? Or conversely, are you going to vote for Trump, yes or no? I know there's some third candidates, but let's keep this simple. So in that case, all political polls, and I don't know if you remember I mentioned this the first week, are based on 1,000 registered voters. Of course, likely voters are better than registered voters. So in that scenario, 1,000 out of what, I don't know, 200 million or something, really is a good statistical sample size for polling, and that is the default. So you'll be getting a little more intro to polling and that 1,000 number in other videos. All right, so back to, because the theme of today is about measurement. I'm measuring something. I'm calculating a mean, and I can get standard deviations. So we already talked about how bigger sample better than smaller sample, and to use as an estimate of the population. But how do we even know that these samples are even close, right? How do we know that? We know it because people tell us it's true, right? But historically, they had to research this. Let's say my hand, I don't have a chalkboard right here, is going to represent the population mean. And we go get these samples. How do we know the samples aren't way up here? Maybe all the X bars are landing way higher than the mean, or the population mean. Or maybe they're all landing way lower or something. How do we know? Actually, it does not turn out to be like that. It turns out that all the samples tend to land around the population mean. And that was a really, really important discovery because it let us know that this idea of taking a sample is actually a pretty good estimate. I'm going to write up some of this stuff in just a minute. And yeah, you know, because you got to understand that idea of depending on what sample I get, it's going to give me a different xbar, right? So I don't even know if the sample I get is pretty accurate or not. In a couple minutes, when I put up the notes, I'm going to talk about taking lots and lots and lots of samples. Actually taking all the possible samples of a certain size from the population. I just want to give you a number real quick. Picture 20,000 JMU students. And when I talk about samples of size 30, make sure you know that I'm not talking about putting them into groups of 30 to do group projects or something, right? All you have to do is change one person in that sample and it makes it a brand new sample. So you could leave 29 of the students the same, remove, let's say, John and put Mary back in there instead of John, and that is considered a different sample. So when I say take all samples, we are talking a massive number. So I'm going to run a number for you. You don't have to know how to do this. If you took AP Stats, you know what I'm about to do is a combination. I'm about to calculate how many different samples of size 30 that I could take from 20,000 JMU students. All right, picture the number 4 and put 96 zeros after it. 96 zeros. That's beyond what my brain can comprehend, right? There you go. That's the number. See those 96 zeros. Think about it. A million has 6 zeros. A billion has 9 zeros. A trillion has 12 zeros. We're talking 96 zeros. We're talking trillions and trillions and trillions, right? So massive number. So everything that I'm about to put on the board is based off of that you went and looked at that many samples. How am I going to show you a trillion things on the whiteboard right now? I'm not, right? So we're going to start with a really, really made up, not real life problem, but something that's doable at the whiteboard. So let me write up some of this stuff. It's part of the lecture notes for this. Just kind of write some of what I just said. So the thing, I love the word thing, don't I? The thing that is describing the population is called the parameter. It's just a fancy word. So we use samples to help us estimate the population parameter, or in other words, the theme for today is to use xbar to help us estimate mu. But xbar is going to change depending on who's in my sample, right? We call that a random variable. Again, fancy word to say, yes, it's going to change from sample to sample. What if we took lots and lots of samples and got lots of xbars? So from all these different samples that I take, I calculate the xbar for each one, and I make a list of all the xbars that I got, okay? Make sure you know any xbar is rarely exactly correct. I mean, for the xbar to actually be completely, perfectly equal to the mu would be very surprising. I mean, we do hope it's in the ballpark. And I had mentioned, of course, we understand intuitively that larger samples are more accurate, but they're costing me time and money, so we've got to find that balance, right? All right, let's do a tiny little example. Well, let me write up one more thing of notes before I do that. What we're talking about today is called the sampling distribution. Fancy word for what does it look like? Sampling distribution of x bar. And what that means is we're going to take all possible samples of size whatever, of size n, for example, I mean, I don't know if we're talking 30 or 10, but size n, get all the x bars and graph it. And what does it look like? What does this look like? This is what they had to do historically. So this is where I told you, right now it's going to seem kind of confusing, and where is she going with this? Hang in there with me. I'm trying to give you a little background that they had to do this originally to make sure that the x bars basically were in the ballpark of the population mean. So I'm going to attempt to prove something to you, but it's going to have to be a tiny population, like 3 people, which we would never do in real life. If we had a population of 3 people in real life, we would just go ask those 3 people whatever we need to, right? But it's something I can do on the board. So I call this my tiny example. Let's say I have 3 people and I ask them, how many dogs do you have? Jay has 2 dogs. Teresa has 0 dogs. Kyle has 3 dogs. Okay? This is my population. I only have 3 people. Okay? Now go with me here. This is called pretend time. I showed you my population. In real life, you never get to see the population, right? So actually, while we're here, we could go ahead and calculate what the population mean is. Well, it's 5/3 or 6 repeating, right? But here's the thing. In real life, you're never privy to what the mu is. You have no clue, right? Well, let's just kind of tuck that away. Pretend I hadn't shown that to you, okay? We're going to take all samples of size 2. Again, you would never take samples of size 2 from a population of 3 in real life, but it's small enough for me to do on the board. All samples of size 2. So you could have Jay and Teresa. You could have Teresa and Kyle. Or you could have Jay and Kyle, right? There's only 3 different ways for me to choose 2 people from those 3. All right, Jay and Teresa, their average, their sample mean, 2 plus 0 divided by 2. 2 divided by 2 is 1. Teresa and Kyle, 3 plus 0 divided by 2. Their sample mean is 1.5. Jay and Kyle, 2 plus 3 divided by 2. Their sample mean is 2.5. So this is just what we were trying to say, that the x bars vary, right, from sample to sample. And that's kind of a big difference. Now, again, I'm letting you peek at my population. This is like my, what do you call it? The magic ball or whatever. So I'm letting you peek here. Since I'm letting you peek, I can sit here and say, okay, that one underestimated, that one was the closest, and that one overestimated, right? But in real life, you never know what the population mean is. So when you get a sample, you don't know that the sample you got was the closest or if it was a little above or a little below. So it almost sounds like I'm telling you that taking samples is not a good thing. But there's a much more interesting result. This language you're not going to like, but it's the way we talk. And you're not going to like the notation. What is the population mean of the sample means? I know that sounds like Greek to many of you. This is a subscript, okay? So this is important notation. This is not mu times x bar. This is mu subscript x bar. And this is what this means in words. The population mean of the sample means. What does all that mean? What is the average of the averages? What is the mean of the sample means? 1 plus 1.5 plus 2.5 divided by 3 is 5/3 or 1.6. This is not coincidence. This was the first big result that they discovered. And you're probably still sitting there saying, who cares and why does it matter? I might be able to draw you a picture that will help you understand why this was really important. This result said, yes, your samples are in the ballpark. Remember earlier I was using my hands? We wanted to make sure that if the population was here, like all the samples weren't way up there, or if the population was here, that all my samples weren't way down here. We wanted to make sure the samples were around the population. That's what this does for us. So let me try to show you maybe graphically. So if we go and graph all of the x bars, this is no longer an x. When we were doing test 2, we were talking about x stuff. Now we're talking about all the x bars. Remember my thing with 96 zeros in it or whatever? Okay. What that says, the result from just a second ago, is that yes, all of the sample means are centered at the population mean. They're all in the ballpark. We would, again, have hated for mu to be down here and all my x bars to be up here, right? Yeah, that's not the case. They are all around it. Yes, some are going to be below. Yes, some are going to be above. But most of them are absolutely right around the truth. I'll use the word truth a lot for population. So this is saying, yes, your samples are centered around the population. That really was an important thing. Now, while I have this picture up, bringing something back from test 1, I think, obviously, we would like green better. Well, even better than that. Red's even better, right? What am I doing? I'm shrinking the standard deviation. The red curve is better than the black curve because it has smaller variation, smaller standard deviation. Well, unfortunately, I cannot prove to you the standard deviation formula. So I'm going to just have to give it to you. So from a minute ago, we said, okay, the mean of all the x bars is the population mean. The standard deviation of x bar, meaning does it look like the black one, the green one, or the red one, is the original standard deviation divided by square root of n. There's that sample size coming into play. Let's talk about this mathematically. Maybe I should go over here. You don't have to write this. If you have 1/2 and 1/4, which one is smaller? This is smaller, right? Because that's 0.25 and that's 0.5. That's a smaller number than 1/2. When your denominator is bigger, your entire fraction is smaller. When your denominator is bigger, your entire fraction is smaller. When you raise the sample size, the standard deviation goes down. So I can tell you that the red curve would be based off of a larger sample size than the black curve. Again, that's taking time and money, right? So we've got to find which curve we can afford and what we're happy with. I took a little freedom here. You probably wouldn't have known it. I drew this unimodal and symmetric. How'd they know it looked unimodal and symmetric? Well, that was something else that they studied. And let me say this, we certainly hope X bar is normally distributed because, I don't know if you've caught on, this is the only piece of paper we have with actual areas on it, right? I didn't give you one of these for skewed right and another one for skewed left and another one for bimodal. This is all we have. So the only problems that we can work with are the ones that are normally distributed. So then I can pick up this z-chart. So this z-chart is back. So if you missed those problems on test 2, you really need to back up and learn that before you continue with test 3 material. All right, so how do we know that x-bar is normally distributed, or when is it, I guess, is a better? This is called the central limit theorem. I don't really care that you know that word, but many people do in the sciences and mathematics, so if anybody ever asks you if you studied it, please say yes. Most people call it the CLT for short. Basically what it says, if the original x distribution is normal, then when you take samples, they're normal. If the original x is normal, then the x-bars are normal. Not that interesting. If I go study adult female heights, which I know to be normally distributed, if I take samples of adult females and I graph them, they're going to be normally distributed also. But remember those problems when we were talking about skewed? I said salary and house prices were skewed. We haven't been able to study those types of distributions because they've been skewed, right? Well, we now can because of the second way to know that x-bar is normal. Please know that this is an or. You don't have to have both of these. You have to have one or the other. That or is really important. Here's my magic number. It's probably the first magic number. If n is greater than or equal to 30. It's almost as simple as that. Now, obviously, this is an intro to statistics. In real life, we do further tests to make sure we have normality. But believe it or not, that's a really wonderful rule of thumb. Like, if you just have something slightly skewed, you could probably get away with 25, 24. If you have something that's a pretty good, ski slope, really skewed, 30 is going to do it. Now, if you have something freaky, like a roller coaster going up and down, no, 30 is not going to do it. But what's interesting is, in real life, most data doesn't turn out to be like a freaky roller coaster. So most of the time, that actually really does work in real life. You absolutely need to memorize this or know this, because often on test 2, but all the time on test 3 and test 4, I'm going to be asking you, how do you know x-bar is normal? And you're going to be using this. So this is something that's going to get you through the rest of the semester. Let's try to put all this into a nutshell. Then we're going to practice a problem. And again, I promise the problems go much easier than probably what this looks like so far. Using a lot of shorthand notation, and I want to show you what's on your cheat sheet and what is not on your cheat sheet. I'm going to let you write that down for a second. I need to grab my water. First, before I make sure everybody understands what that says, this part right here, you don't even have to memorize. It is on the bottom of the cheat sheet. See right here? This right here, that one is, I think, going to be the next video. This right here stuff is sampling distributions. This was the notation we were using from test 2 for the individual x, right? We said what comes before the comma is the mean, what comes after the comma is standard deviation. We already know this guy. This is the new one I've been presenting for the last 25 minutes. That if you're taking the sample mean, the mean of both of these is the original population mean. Remember when I drew the curve and I said if you graph all the x bars, it's centered at mu? Remember that? That's what that is saying. And then I just had to tell you the standard deviation formula, and it has the sample size in it, right? And I'm just reminding you really quick, how do you know it's normal? If the original x was normal, or if n is greater than or equal to 30. Now, here's the thing. Some of the x stuff from test 2 is absolutely on test 3, because part of what I have to do is make sure that you can read a problem to know, is it an individual x problem or is it a sample size problem? And it's really easy to tell the difference. So just kind of pointing out the good news visually, whether it's test 2 or this new test 3 material, same mean. Look, the only difference is this right here. Instead of using sigma, we're going to use sigma over square root of n. Remember how in test 2, we went forwards and backwards like that, right? Well, we're going to do the same thing now. We're just going forwards and backwards with the x bar. The exact same thing. How do you get z-scores? Same way we got them there. Subtract the mean, divide by standard deviation. This is the mean. This is the standard deviation, though, that time, right? And you can go forwards and backwards. So the exact same process. So just to show you how similar it is to test 2 material, I'm actually going to split this board and do kind of 2 problems at once. A new problem versus an old problem. That way you can kind of compare the language. I'm revisiting the cork problem from handout 9. You do not have to get that out. That problem, where's the original problem? Hold on. Oh yeah, sorry. It said diameters were normally distributed. I think it was 3 centimeters and 0.1 centimeter was the standard deviation. So that's all you need to know. I'm revisiting that problem. All right, let me write up the 2 pieces. Okay, example 1 says, what's the probability a cork is less than 3.05? Example 2 says, when sampling 25 corks, what's the probability their mean is less than 3.05? So, just like visually comparing the 2, you can definitely see a difference here. I mean, this one's shorter and that one's longer, but a little more to it than that. In the English language, a means 1, right? This is just the individual x. That's test 2 material. But look at this one. Here was the first red flag, or whatever you want to call it, that hit you over the head. It said we're sampling 25 corks. Okay, then n is 25. As important, I have to hit you over the head again, because I have to word the question appropriately and correctly, right? The probability their mean. That translates to x bar. I'm asking you a question about x bar there. And if I'm asking a question about x bar, I have got to give you the sample size, the n is 25. So this is test 2, this is test 3. But you would still be responsible for something like this on test 3 also. I'm going to speed through this one since it's old material. X less than 3.05. I have to subtract the mean, divide by standard deviation. Oops, I'm so sorry. That's supposed to be a z, because I'm at the z level, right? That turns out to be a z-score of 0.5. If you look him up, it's 0.6915. Okay, so hopefully I didn't lose you there, because that's test 2. I do assume you're perfectly fine there, or I will lose you over here. Okay, this is xbar. So whenever I see I have an xbar problem, I do kind of want to breathe for a minute and just do a little bit of side work. All right, first of all, how do we know xbar is normal? Because if it's not normal, I don't have a problem to do. Don't sit here and think, oh, but the 25 is less than or equal to 30. That has nothing to do with it. Remember, the first way to know is if the original is normal, then the x bars is normal. So, because original x is normal, or you could just say, there is a shorter way to say it. It stated normality. So if I'm asking you on a test, you can say, it stated normality, or it said x was normal, something like that. All right, I'm still kind of doing some scratch work here. Now, again, you don't have to memorize. A lot of students don't use their resource. We know we're doing an xbar problem. Pick this up. You're like, oh yeah, okay, the mean is still 3. Oh, but I gotta calculate a different standard deviation. The standard deviation is 0.1 divided by square root of 25. The standard deviation is 0.02. Nobody wants to carry around a fraction and a square root symbol, right? So please, and these are going to be small numbers, 4 decimal places, but honestly, it's 0.0200, so I'm good. That's the standard deviation we're using. Okay. All right, well, now what did they ask me? They want to know the mean less than 3.05. Okay, I'm going to turn x bar into a z like I've always done. How do I get z-scores? I subtract off the mean of x bar. Oh, that's the same thing anyway. Divide by the standard deviation of x bar. At this point, the process is exactly what you did on test 2. Excuse me. I'm going to pause for a minute, but I'm going to keep talking. Because I really want you to see what's happening here on the board. Look right here, these two problems. X less than 3.05, I subtracted the mean because the means are the same. The only difference, look, this denominator and that denominator is the only difference in these problems. Well, I mean, of course, the answers are different. That's the only spot. So calculating that new standard deviation for x bar is critical. So unfortunately, sometimes students miss this on my test because to them, they're thinking, oh, I just missed one number. They'll use that one, it's not right. But I'm like, that one number is the entire problem for you to know that this was an x bar problem because they gave you a sample size and they asked you a question about the mean. So unfortunately, it's a lot of points off if you don't use 0.02 there. Let's do another whole problem start to finish. Okay, let's say we're telling you that test scores on some particular test are skewed. The mean is 84, the standard deviation is 3, and I'm going to sample 31 students. So let me and then it says probability their mean is greater than 86. But let me tell you something. As soon as I read test scores are skewed, I immediately knew what type of problem this had to be. This cannot be an X problem because we can't work with skewed distributions. So I immediately, when I read that, I'm like, you better not ask me anything about X. It's fine, you gave me mean and standard deviation. And also I'm thinking, if you ask me any question, you better have a sample size greater than or equal to 30. And I was like, yep, I knew that 31 was coming. And yes, I knew they were going to ask me a question about the mean. So you've got your N here. You have the question about X bar here because this is an X bar problem. X bar is normal. The mean stays the same. The standard deviation is the original standard deviation divided by square root of N. 3 divided by square root of 31. Let's figure out what that is. This guy is 0.5388. So I'm not going to be using a standard deviation of 3 when I do this problem. I'm going to be using a standard deviation of 0.5388. How do I know it's normal? Because 31 is greater than or equal to 30. On a test, if you simply say N greater than or equal to 30, I'm going to take off. You have to show me that you know what the N is. Because I can't tell you how many people in this problem will think that they're comparing 84 to 30, and that is not what you're doing at all. So you have to show me that you know what the N is. All right, so at this point, pretty basic problem. We're doing X bar greater than 86. I'm going to turn the X bar into a Z. How do I get Z scores? I subtract off the mean, divide by standard deviation. That new standard deviation I calculated. This will give you a Z-score of 3.71. At this point, it's old stuff, right? It's test 2. You go to your Z-chart, you look up 3.71. You're going to see 0.9999. But I've been staying organized. Maybe I should use green. I've been carrying around my greater than symbol. Why? So I don't forget to subtract from 1 at the end to get my final answer of 0.0001. I am going to do a part B to this problem. All right, so pause me if you're not ready for me to erase. Let's do a part B. You know, I'm going to leave that here because I still need that number. Part B. All right, so I see this is working backwards, right? They just gave me an area. I mean, I know, of course, I'm still doing an X bar problem. They're talking about the means. But when they give me an area, this is going to be A to Z to X bar, right? So right now, I want you to do 2 things. Well, 3, because I want you to pause me. But I want you to pause me, and I want you to see how far you can get on this problem. Because honestly, most of this problem is test 2. I particularly want you to draw a picture. A lot of people get this problem wrong, and so then when you unpause me, and if you did get it wrong, you can kind of see where you went wrong. So pause me now, give this one a try. All right, so let's start with that picture. And what word is back? At least. So many people miss this on test 1 and test 2, and it's going to be back on test 3. So let's draw a quick little picture. I know my mean is 84. That's supposed to be unimodal and symmetric. At least means go bigger. Remember, I only have 2 choices. Is the boundary there or is the boundary there? Which line, red or green, has 63% bigger than it? Oh, not that. That's not 63%. That can't be right. Here is your picture. This is the 63%. That's not the way my Z-chart wants me to talk to it. Remember, my Z-chart always wants to know who lives on the left of the fence. So this is the area we have to be dealing with, which I guess is 0.37. So your area is not 0.63. It's 1 minus 0.63, which is 0.37. Remember, this is an area, not a z-score. That was another mistake I saw on test 2. So again, anytime you write an area, if you want to make it 4 decimals, to remind you, you're having to scan the body of the chart to find the z-score. When you look for 0.37, I'm looking as if I'm a student. I had stopped at 0.3669, but then I checked the neighbors. 0.3707 is best. So that's actually the area that you're going to find. You're not going to find him. And when you find him, it is negative 0.33. The z-score is negative 0.33, which makes sense. I knew I had to have a negative z-score, right? Okay. Equals. I don't know what x bar is. I know the mean of x bar. I know the standard deviation of x bar. Right? So here comes this guy back down there again. You're not using a 3 down there. You're using a 0.5388 because this is an x bar problem. It used the word mean. I had a sample size. You do your algebra. 83.82 is the answer. I was expecting an answer less than 84, of course. All right. So I think I can write it up. At this point, I'm sure it's on the homework sheet and my test 3 schedule and all that, but might as well tell you, you're going to do handout 9, all of number 3, 4, and 5. I'm aware that you already did part A for test 2 material. I don't care. Pretend you never did it. I need you to do all pieces of those 3 problems, and of course the answer key is posted. All right, next time we have one more sampling distribution to do, so that will go quicker because I don't have to give you the whole introduction of sampling distributions to begin with, so we can just kind of get into nuts and bolts. All right, see you soon.